Hello, everyone. Welcome to lecture 11 in ECE 576 in our fall semester. I hope you're all doing very well. This is our last lecture before the Thanksgiving holiday. And a few announcements before we start our discussion today. So one is regarding the quiz number 6 that you had recently. So it had two problems related to marginal independence. So just asking you whether two variables are independent or not. And some students struggled with it, and I feel like I didn't make that very clear in the Bayes net lecture. So I will remove those problems from the quiz, and I will also give you a description on that today to help you identify marginal independence. So quiz number 6, basically Q3 and Q10 on marginal independence will be excluded from grading, right? Or in other words, everyone will be awarded full score on that two parts.
I have a quick question on the quizzes and the homeworks.
Yes.
So for this quiz, it was 15 points, or is that going to be normalized to 10, so it's worth the same as all the other quizzes?
Yes. So
and same with the homeworks?
Exactly, yeah.
Thank you.
Yeah, so these numbers are just to, kind of make the grading fair, like every part or every question is worth 1 point.
Yeah,
that
makes sense.
Yeah, but that'll be normalized, and we will drop one quiz and one homework from the final grade. So let's also write this announcement. So I've received some requests on people trying to, improve their homeworks or quiz grades. So, so to make it fair for everybody, one of your worst quiz and worst homework will be removed from the final grade. And the third announcement is about the project midterm or project mid-review. So I see some people have not submitted their mid-review reports, which was due last night. So what I'm going to do is
Professor, the date that you had was for tonight, for the 16th at 11:59.
Yeah, that's correct.
Yes, okay, so that's due tonight. So make sure you submit it by that day. So today, right?
Yeah, I think
Yes,
it's today
correct.
at midnight.
Today is the 16th. Okay. All right. So basically make sure you submit. Otherwise, you will have 5% deducted from your project score. So just to make sure that everybody submits their mid-review. So it's not graded. You're not penalized for submitting something which is not up to the mark. But if you don't submit it, then there's a penalty. Okay. And now I want to talk a little about the quiz number 6 and some of the parts where people had problems and I received emails. One of them was this marginal independence thing, which I unfortunately forgot to talk about in the lecture. So as a general principle, when you're talking about Bayes nets, basically, if nodes are connected, that does imply that there is some dependence, right? So if two nodes are connected in the Bayes net, you can obviously see the dependence. And if they are disconnected or de-separated, right? So it does not imply that they are independent. So that's the critical part. So this is not true. If you say that two nodes are de-separated, that does not mean that they are independent, because the whole problem is because de-separation is only sufficient to conclude the conditional independence. Okay, so it doesn't say anything about being independent. So for example, in this question, if you write the joint probability, I mean, obviously the I and the H may be independent, but other variables like T and H, so for example, this and this may not be independent unless there is the condition that their joint probability is the product of the individual. So unless this condition holds, which you can actually verify from the tables, in general, it is not true that they are independent or not, even if they are de-separated. So de-separation is not sufficient to conclude independence. Okay, so for more details, you can refer to a document which I also have it at the end of this. Okay, so how do I get rid of this? Anyway, I have, so let's say the appendix at the end. So I have an appendix at the end, which I can also read out to you here. It's about the marginal independence in Bayesian networks. And the idea is, in general, de-separation algorithm helps you to figure out conditional independence, but the other question could be, are X and Y marginally independent? Now, the process to determine this is the following. So you draw the ancestral graph, okay? And this is actually the reduced version of the original net, consisting of only variables mentioned and all of their ancestors, okay? So you forget the descendants. Then the next step is to moralize the graph by connecting the parent nodes. So if there's a child node, then their parents are automatically connected. So people call them moralization, because it's like marrying the parents. And then the next step is disorient the graph by replacing the directed edges with undirected edges. Finally, you delete the givens and their edges and read read the answer of the graph. So if variables are disconnected in this graph, they are guaranteed to be independent, right? So this statement is important here. If variables are connected, then they are guaranteed, they're not guaranteed to be independent, but they can still be, because it says that if their joint density is equal to the product, then they can still be independent. So there are a few examples here in this handout. I can also read them out to you quickly. So for example, if you have a Bayes net, you have answered questions, but the question important here is number 5, which is, for example, this one. So are D and E, are they marginally independent? So let's go to their solutions. So for example, this here. So first step was to draw the ancestral graph. So you got rid of the descendants of D and E. And the next step is moralization, which is just for every child node, you just connect the parents. Okay, so that's the moralization step. And the next step is to disorient, meaning you remove the arrows. And finally, you delete the givens. So are you given something, meaning is it conditioned on something? In this case, no. So you leave them as it is. Now, if it is given, then you remove that node and all the edges connecting that node as well. So in this case, nothing gets removed. So the answer is no, because D and E are connected. So they are not required to be marginally independent. So they are not required. I mean, this is the important thing. They can still be independent if the numbers say so. But from the structure, you cannot say that they are in any way fully independent. Okay, so this is an interesting handout. I think you can go through it later on and also see the other examples on different queries that you can make out of this Bayes net. So let's go to our quiz and figure out the rest. The other 2 questions, most of you figured it out, but some students were still having troubles. So let's try to do it quickly here. So this question asks whether I and H are conditionally independent. So we're looking at I and we're looking at H, and we are given E. So first thing I know is that in this situation, it will open this path, right, from the D separation algorithm. So the question is whether there's an active path between I and the other thing is also this path. Yeah. So so if you look at it, this path gets open and there's no obstruction. So because they are connected through an active path, then we can say that they are not independent. So if the question asks whether they're conditionally independent, the answer is no, because of an active path, which is I, T, E, U, and H. Right? And the next question also follows a similar line of argument, where the question is about T and H. And again, this is E, right? So obviously the path from here is blocked, but there is an active path that sits from here. Okay, so following the same argument, we can say that they are not conditionally independent. Which is from T to E to U and to H. So that's all that I wanted to talk about regarding the previous quiz. If you have questions, let me know. Otherwise, we can move on to today's topic.
Question number 7, Professor. So it's similar to 6, but it introduces more variables. Does that?
Which,
So,
okay,
7.
1 second. So question number 7 is asking E and H.
Yeah, so I treated it as
U, I, T.
yeah.
Okay,
if
so,
you had-
okay, let me just copy this and show you the problem. So it's again, this time it's E and H. Right, and you know I, and you know T, right? Okay, so I mean, the first thing is the direct path is immediately blocked because it's a cascade link, right? So this is blocked. Now looking at the other, I mean, this is an open path, but this is again blocked. So there's no way you can go from E and E to H, right? Both your immediate neighbors are blocking you. Do you see this?
Yeah. No, I got
So
confused when you say given, then you can observe this given variables. So that's where.
Yeah, I mean, when you observe something, that means you just shade it, right? In this algorithm. Am I right? Okay, I think.
But then in this case, you're saying that's true or that's not true?
It is true because every path is blocked, so they are.
Yeah.
So you can actually mention. So there's deseparation between them, which helps you establish conditional independence. Okay, so let's move on to today's topic, and we are going to study an analog of Bayesian networks. So when we talked about Bayesian networks, we said, so let's write a refresher. So we said it's an acyclic and directed graph. So two properties. One is the direction, and the other is being acyclic. And when I say acyclic, that means if you take an example of 3 nodes A, B, and C. and two scenarios. One of them, the arrows are like this, and the other case, the arrows are like this. So, so this is a Bayesian net. But the other one is not a Bayesian network. So does anybody know why? Any ideas on why that is not a Bayesian network?
Is it because there's no start and end?
No, I mean, the idea is it's cyclic. So there is a cycle, right?
Yeah.
Yeah, in some way, what you said is right, but it shouldn't have cycles. And the reason is because there is a factorization method where you have CPDs or conditional probability distribution. So when you wrote the joint density, it is just a product of the CPDs. So in this case, you will have a never-ending CPDs, right? So let's say the joint can be written as the product of the CPDs, which says the probability x1, x2 up till xn is actually the product of the probabilities which are xi given the parent nodes of xi, right? Or let's say I belongs to all the nodes in the network. Okay, so that's what we saw last time, and today we're going to look at the undirected variant of probabilistic graphical models. So that's the topic for today's discussion on just like directed graphical models are called Bayesian networks, these are called Markov random fields. Or MRF. Okay, so it's an first of all undirected graphical model, right? So represented undirected graph, and we have one node for each random variable, right? Just like the Bayesian net. But we do not have that parent-child relationships, so we cannot really express it as a product of those CPDs. So there's no CPDs, but instead there's something called potential functions. So instead of CPDs, we specify non-negative potential functions. And these functions are over sets of variables associated with the cliques. Again, keyword cliques of the graph. And these are referred by C. So the joint density can be written as the product of all the potential functions normalized by a factor. So it will be probability x1, x2, all the way to xn is actually 1 over z times the product over all the cliques and the product of the potential functions. Okay, so this part here is the potential function of clique C. Okay, small c. So we have may have multiple cliques in the network. So every clique will have a different potential function, and if you take the product and then normalize by z, so this thing here is the normalizing factor, meaning that it converts it to the probability between 0 and 1. It's a normalization factor, and or also called partition function. Okay, so essentially the factor z just normalizes the distribution. So z can be computed as the product of all the cliques. So the partition function can be written as z equals the sum of all these products. So if you have potential functions then let's say these cliques are x hat, then you have to sum over all the x hat. Okay, now just like the CPDs, actually the potential functions can also be represented as a table. So like CPDs, the potentials can be represented as a table, but it is not normalized, right? So the values can be anything and doesn't have to be adding up to 1. So okay, so this is a brief introduction of Markov random fields. And when I say cliques, basically here's a figure that tells you what are cliques. So actually, if you look at the description first, maybe that's more clear. So for example, if you look at this graph, then these red dots basically form a clique in clique of size 3 in this graph, right? So so all these different shaded red triangles are actually the cliques of this larger graph. And in the next figure, you can look at a graph of size 5, sorry, 6 nodes, and it has 3 cliques, 5 different 3 cliques. So for example, if you look at the first one, nodes 1, 2, and 3 form a clique, right? And then 2, 3, 4 form another clique. And then 2, 3, 6. So this forms a clique, and then 2, 4, 6 forms another clique. And similarly, 3, 4, and 6. So 3, 4, and 6 also forms a clique of size 3. So in some words, it is like a sub triangle within the graph. So formally, if you look at the definition, a clique of size k is actually a subset of the k nodes of the Markov random field, so that each pair, which is part of the subset, holds that x and y are connected by an edge. So it's the pairwise connections between them. So if you look at the a 3 clique, you will see that every pair has an edge between them. Okay, so cliques can be of size 1, size 2, or size 3. Okay, size 4 wouldn't make a clique unless unless everybody is connected with everybody, right? So size 4 can only be a clique if this is there and this is there, right? So that's a clique. That may also be possible, but generally we do not have that type of graph. Okay, so if you look at this diagram here, it only has one clique of size 3. So, which involves x2, x3, and x4. So that's one clique. And if you look at cliques of size 2, that would be x1, x2, x2, x3, x2, x4, x3, and x4. So these are basically these links. These are cliques of size 2. And again, the rule is that every pair within that clique has to be connected by an edge. And finally, you can also have cliques of size 1. So that's kind of the nodes themselves. So this is a clique by itself of size 1. Okay. Now, what we said earlier is that the factorization of the joint probability can be written as the product of all the cliques. So for example, here's the joint probability density function of a graph where the cliques of the graph can be represented by potentials. So there will be a potential phi c for every clique. So xc will represent the nodes that are part of that clique, and you take the product of all those potential functions. Now, the normalization constant z can actually be this product over all the possible cliques in the all the possible nodes in the clique. So you sum over all the xi's. So we will see this with a numerical example here. So imagine you have a graphical model of 3 nodes, which is undirected. There's no arrows here. Just A is connected with B, B is connected with C, and C is connected with A. So if you look at this, you need to have potential functions for every clique. So in this network, I mean, there's only 1 3 clique. So let's use a smaller clique, which is a pairwise. So every pair is a clique, and for that we need a potential function. So we will have 3 potentials here: phi AB, phi BC, phi AC. And the potentials look like this. For example, for A and B, if A is 0 and B is 0, we have potential value 10. Otherwise, we have potential value of 1. And same thing with A is 1, B is 1. We have high potential if both A and B are the same value, right? 0, 0 or 1, 1. Otherwise, we have a small potential value. Now, same thing with BC. Again, we have a high potential here, a high potential here. And AC also has the same. So in other words, this graph, what it says is like, the link is stronger if both variables have the same value, right? So in other words, it's not the it's trying to encourage that the adjacent variables take the same value, right? This is the type of potential that is designed for this network, and it says potential function on each edge encourages the variables to take the same value. Okay, so now as we said, the joint density function can be written as a product of potential functions and with a normalization. And this is a a product of potentials. And these are like cliques, 2 cliques. Okay, now the normalization factor is actually the sum of these potential functions for all the values of A, B, and C. Right, so you sum it over all possibilities. So if you compute it, the sum basically, it will turn out to be 2060. And then, I mean, you can do it by I mean, a computer can help you do it, but intuitively, even if you look at this, whenever A, B, and C have the same value, then it is kind of 10 times 10 times 10, so there will be 1,000. And otherwise, if they are different, there will be like 10 times 1, which is 10, and this occurs 6 times, this occurs 2 times, because 0 and 1, right? So it's like taking the product and sweeping all the values of A, B, and C and finding the sum. So that's normalization. So essentially the joint density function is 1 over 2060 times this product. Okay, so that's the way you do it for Markov random fields, and hopefully if you want to do inference, that's the next step where you will compute either some conditional probability from this graph. And again, once you have this form, then you can actually go about finding those conditional queries or inference questions. Now, if I take an example of it's a hair color example. An example goes the following, that there are 4 people, A, B, C, and D, and everybody can have a choice of color for their hair, which is red, blue, and green. Now the connections between them are designed in a way that it's incentivized to have the same color of hair if they are connected. But again, these are probabilistic. We can only say that it's more likely for A and D to have same color, A and B to have same color, and B and C have same color, and C and D having the same color. Okay, so if you have this type of a network, the joint probability distribution can be written as the following. So it's all the cliques. So the cliques are AB, AB, BC, CD, AD. Okay, these are the 4 cliques of size 2, but then you also have single node potentials, which can actually go into the normalization also. So these can also go here, right? So it's like a relative thing. If you know the node potentials, fair enough, you can put it up in the factorization. If you don't, then you assume that they are part of the normalization, factor Z. So pairwise potentials enforce that no friend has the same color. So sorry, I was saying the opposite, but so phi AB is 0 if A and B are the same, and it is 1 otherwise. And single node potentials say what is the probability of having a particular hair color. So for example, phi d of red is 0.6, phi d of blue is 0.3, and phi d of green is 0.1. But it's important to note here that these numbers don't have to be probabilities, really, because at the end of the day, there's a variable z sitting outside, and that can normalize everything. So important thing is the normalization makes the potentials scale invariant. So what that means is your potential values can be, as an example, 6, 3, and 1 by just multiplying everything by 10. And we could do this because there is a factor z, which will eventually normalize everything. So it doesn't really matter. You don't have to have potentials which are probabilities. So that's where the flexibility comes in. If you're designing a graphical network, you can actually set potentials that just provide the relative strength, just like molecular bonds. So if you have molecules, you can create a bond between them and assign some strength to it. And you will see how these models are actually used in physics-based models and machine learning models. That's simply because of their scale invariance. Now, the next idea is about conditional independence when it comes to undirected graphical models. So if you remember, in the Bayesian net, we had an algorithm called d-separation, and that was helping us find conditional independency statements. And the benefit of doing that is we could simplify our joint probabilities from the product of all the CPDs to just the relevant CPDs, because some of them may be independent given certain variables are observed. So if you look at the Markov random field, it's a little different. So imagine you have a graph G, which is undirected, and you want to figure out conditional independence. So in this case, you will have to look at graph separation. So graph separation means that if you observe some random variables and you remove those from your graph, does it separate your variables? So for example, in this figure here, what it says is that, so any node in XA is independent of any node in XC given that XB is observed. So the statement is that if there is no path from A to C after removing all the variables in B, then you can say that they are independent. So for example, I can pick anything here and I can say it is independent of anything here given these two. So given these two variables, these can actually isolate the two subgraphs. Okay, so if you look at the previous example, we can come up with some conditional independence statements. For example, so here's one statement which says D is independent conditionally from B given A and C. Right, so if you condition on A and C, basically you will get rid of this, you will get rid of this, this. So then there remains no link between D and B. So D is conditionally independent of B, given A and C. And the same thing the other way around. So A is actually independent of C, given D and B. So the same idea. If you remove the nodes D and D from this graph, along with their edges, there is actually no path between A and C. So they are conditionally independent. And there is no other independencies implied by this graph. Right, so no, that's the only two conditional independent statements we can make. And just like the Bayesian net, we said if two networks had the same conditional independency statements, then they are equivalent. And the same idea here, we can call two networks kind of equivalent if they have the same conditional independencies statement. All right, so when we talk about conditional dependencies, the natural kind of extension to it is a set of nodes. If you observe those, then that kind of isolates a node from the rest of the graph. And that idea is called a Markov blanket of that variable. So imagine if you have this variable x here, and you observe the immediate neighbors of x, then given x, basically, you are actually independent of everything else in the network. Right? Because the whole idea of determining conditional independence is that you remove the observed nodes and their links from the graph, and then see whether things are connected or not. So that brings the idea of Markov blanket. So if x is independent of everything else in the network, given the Markov blanket, right? So U is kind of the minimal set of nodes that needs to be removed. So if you remove U, then X is independent of all nodes minus X minus U. I mean, this is like all nodes. So all other nodes where U is the Markov blanket. I mean, this diagram gives you a better view of what is happening. So if X is a particular node, then its Markov blanket will be really the immediate neighbors, right? So its neighbors in the graph are the nodes in the Markov blanket. And again, the statement is X is independent of the rest of the nodes in the graph, given its immediate neighbors. Now we can look at a quick proof of independence through this Markov blanket idea. So let's say you had a cascade network A, B, and C, and there is no arrows here. So the joint density function is actually the product of all the cliques, clique potentials, and normalized by the factor Z. So here in this case, it will be phi AB and times phi BC. And there's 1 over Z here. So we show that A given B can be computed only using phi AB. Okay. So let's write down probability A given B. If it is only a potential of A and B, then in some way it implies that an that a given B, A is independent of C. Okay, so we are observing B, so we want to show that A is independent of C, which in other words means that there is no C in this probability. So let's write down phi, the probability of A and B, which is 1 over Z times the clique potentials summed over C. So it's like a marginalizing over C. This factor here is like summing out C, right? So in other words, this is like the sum over C of the probability of A, B, and C. And this is like the double sum over A and C, right? That's exactly what it is, right? So the numerator, you sum out C, so that will give you a marginal A and, sorry, the joint distribution of A and B. The denominator is a marginal, so you sum over A and C, right? So that's here. Now, if you sum over C, basically phi AB is a constant, so it comes out. Normalizing constant cancels out, and the sum moves into here. And in the lower portion, or the denominator, again, you can split the summation on C to the next term, and actually you can cancel these terms. So this and this can be canceled because they do not depend on the other terms. So in other words, what we are left with is just the potential of A and B, and that tells you that A and B are actually, A and C are independent, given B is observed. So more generally, the probability of a variable condition on its Markov blanket depends only on potentials involving that node. So in this example, B was actually the Markov blanket of A. So knowing B actually just gets rid of anything. So even if there's D here, and E here, and F here, it doesn't really matter because B was the Markov blanket. So just given B does the trick. The moment it's given B, then the probability of A given B will be just a potential involving A and B. So this proof is through, I'm not sure if, yeah. So now the next step is the following. So if probability of A given B is like this, then to show that A is A and C given B can be written as follows. The joint will be this, and the normalization cancels out. So 1 over Z and 1 over Z just can be removed. And the marginal of B is actually the sum over A and C. And if you look closely, again, the same idea follows, that you actually split the sum into 2 pieces, and this you can actually group together and say that this is actually the probability of A given B, and this is the probability of C given B. Right, so it's a joint divided by the marginal. And therefore you can actually prove that A is independent of C given B. Okay. I mean, in other words, if this can be written as A given B times probability of C given B, then the independence follows. Right, and that's exactly what we have here.
So A is conditionally independent, right? Of
Yes.
C given B.
Sorry. Yeah, A is conditionally independent of
Okay.
E given B. Now we'll look at the application of this in different fields. So one example of a Markov random field is the icing model. This is a very famous model which is used in physics, and a little bit of history is that it was invented by the physicist Lenz in 1920, who actually gave this as a problem to his student Ernst Ising, and on his name the model is called Ising model. Now this model is, I'm sure everybody has seen this in high school physics, where you study ferromagnetism and in the statistical mechanics portion. So the idea is you depict the spin of the atoms with arrows, and the idea is if all the domains are pointing in the same direction, then that material starts exhibiting some magnetism properties, right? So I'm hoping everybody has some idea of this concept. So if you want to represent this as a probabilistic graphical model, again representing every atom or domain in the form of a random variable and connecting them in a graph, a famous model is this grid model. And this grid model is actually an Ising model, which says if the spin of an atom or a domain is +1, meaning pointing upwards, it is green color, and the gray color represents that it is negative. So it's a binary spin. It can be either upwards or downwards. Now, each atom has the value -1 to 1, but they can actually be represented as a graph where adjacent atoms are connected in that graph. Okay, and the question is, are there phase transitions where spins grow from disorder to order? Right, so an interesting case is where everybody starts aligning up either upwards or downwards. So we can study this using a Markov random field where we can define potential functions for these pairwise nodes. So in the Ising model, what they say is that we'll consider an exponential potential function, and that exponential potential function is of this form. So there's weight Wij times the value of xi times xj. So which means that when Wij is positive, nearby atoms encouraged to have the same spin. But otherwise, if it is less than 0, that encourages for them to be of different spin. And then they also have node potentials, which encode the bias of individual atoms. So every atom, you will have a UI, XI. UI is the weight, and these kind of add up to create the potential of so it's essentially 1/z, the product of exponentials, right? Which can actually be written as the sum, right? So it's a product of xi, xj, right? So it's in this format, but then can be written as a sum of the or the exponential of the sum, right? So it's I and j. It's only over I. So for every, so this can actually be converted to 1/z e to the power sum. Okay, so the point is that if you want to write the joint probability function of this arrangement, you can actually look at pairwise potentials. And it makes sense also because atoms will only affect nearby atoms. And as a whole, if you want to figure out the joint distribution, you can actually split it up into pairwise potentials and then take the product. And eventually the question can be in the form of whether there's a phase transition or not, or other questions which involves conditional probabilities. Now, in this example and the previous examples, we've only seen pairwise Markov random fields, involving only node potentials and pairwise potentials. But we can also have higher order potentials, which are the following. So for example, you can have a potential involving 3 variables. And the potential can be the following, meaning it can have a condition. So if this potential function says that it is 1, so it's an indicator function whenever x plus y plus z is bigger than 1. So eventually what will happen is if x, y, z are binary, then we will force that at least one of the variables takes the value 1. Right? Otherwise, this condition will not be satisfied. Just a disclaimer here that Markov networks will actually hide some of the distribution structure. And I mean, for example, here in this example, if you have pairwise potentials, it actually masks the structure, right? So it kind of tells you everything is related to everything else. So you do not have the understanding of the deeper structure. But again, it has some benefits because you don't have to live in the world of probabilities anymore. You can actually just use potentials, and those can be any numbers. There's normalization that will help you. And interestingly, many machine learning models are actually, especially in image data, they use Ising models. So because this represents somehow a grid structure. So if you look at an image is actually a huge grid of numbers. And imagine if those numbers are random variables, then you can represent them as an Ising model, and eventually a machine learning algorithm can learn the probabilities or the potentials, and you can determine if there is an object in the image or there is some relationships between the two pixels. So these are actually getting a lot of attention, especially in two-dimensional images, image processing and computer vision applications. Now, one more interesting thing is about, can we convert Bayesian networks to Markov networks? Again, if you have Markov random field, it's difficult to go back because you do not have the directional information. But if you already have a directed model, can you convert it into a undirected model? And yes, there is a way, and that way is called moralization. So, as I just mentioned in the first slide, or the first part of the lecture, basically moralization is a process where you kind of connect the parent nodes with an edge. Okay, so if you have a graph that looks like this, a Bayesian network, a moralized version of this will be where you connect the parent nodes and then you remove all the arrows. Okay, so you have to connect an edge between, so it has an undirected edge between xi and xj. If there is a directed edge between them, and xi and xj are both parents of the same node. So in this case, the C was the child node, so we actually connect their parents together, and that's the process of moralization, and we'll convert it to a Markov random field. Okay. Now, when we do a moralization, then we actually lose some information. So there's loss of independence information. For example, if you had this network and you kind of moralized it, then you cannot say A is independent of B, right? I mean, if it is given C, then obviously they are not, but otherwise A and B can be independent, and that statement will be lost if you kind of connected them together. Because previously, A and B are not connected together, so they can still be independent. Okay, so when you kind of convert the Bayesian network to Markov networks, you will also need to obtain potentials. So the way to do it is the following. You already converted the graph to a undirected graphical model, but you need potential functions. So what you would do is just create a potential for every conditional probability distribution. So every CPD, you will have a potential function. If you were in a hidden Markov model that I talked about last lecture, converting it to a MRF is actually straightforward because there is there's no parent node, so you don't have to do any moralization. So essentially, you will just remove the edges and replace them with undirected connections. Right, so that's the whole process of converting it to a Markov random field. But so I think essentially that was the whole idea behind today's lecture, to introduce you to a new kind of a new graphical model that comes in very handy when it comes to representing worlds and set of random variables that do not have a formal structure. So as I told you in images, if you're looking at a grid of pixels, you really do not have a structure in them. So there is no logical arrows or directions. So essentially, they are just connected, meaning the value of one variable influences the other, right? For example, in an image, you will have two pixels are more likely to have the same color. Instead of totally different colors, I would say they are more likely to have the same color. And that kind of smooths out your images. If it is totally random, meaning high contrast pixels, then the image may not be very meaningful. So images in general have this underlying behavior of having similarities between their neighbors in terms of the color. Again, I think materials will have the same property, like ferromagnetic materials will have the same property, and this actually helps you to capture the structure of the underlying network. And if you have that, then you can actually do some inference and do some learning on it. So this lecture is mainly focused on this introduction, and I'll give you a summary of what we have done, what we are planning to do next lecture, and the next one. So we just have 2 lectures left, and one of them is going to focus on doing some inference, so exact inference and approximate inference algorithms. There are many algorithms, but we'll just study one of each, and hopefully that inspires you to learn more when you require it. And after that, we'll have one more lecture on estimating density functions. So again, a couple of techniques to determine what density is if you've given the data. So let me summarize what we've been talking about in the last lecture and today's lecture, and then we will kind of wrap up the lecture quickly. So what we have stressed on is that semantic understanding, right? It's kind of understanding the structure of the problem is actually helpful. So context, if you know the context, it actually helps in constructing probabilistic graphical models that may be directed or undirected. And for directed models, which we called as Bayesian networks, there are properties and rules that help answer some inference queries. Particularly in the form of conditional probabilities then today we talked about Markov random field, and it's a variation or kind of a more expanded model. Field is the more expanded graphical model that helps in capturing general linkages, right? So instead of knowing the exact kind of the causal relationships, we just know the general linkages. We can say it's instead of causal. So causal meaning that you know what causes what. If you know that, then you can create a directional model. But otherwise, you can only conjecture about linkages between variables. So another fact is that MRFs have conditional independencies based on graph separation. Instead of D-separation in Bayes nets. Okay, and we already talked about it, but Bayes nets can be converted into MRFs by a process of moralization. Okay, now just giving you a peek of what is coming up. We are looking at broadly at inference over networks. And generally, it's hard to do. So and that's the whole reason we are trying to come up with conditional independencies and Markov blankets and all sort of things to kind of simplify our graphs, because in practice, these graphical models can be huge, can have thousands of variables, and given each variable has a binary value, can be exponential number of random variables that we may have to look at. So even summing over them to find marginals is not easy in general. So using our properties and graph pruning techniques, we kind of try to simplify the problem first, right? Having a very compact representation of the joint probability distribution, and then we try to do inference in two ways. One is the exact inference, and it is only possible in simple cases. So if you have a smaller and a simpler network, when I mean simpler graph, it means, let's say you have a tree structure. The tree is a simpler graph than any general graph. So in those cases, you can easily do exact inference. And that means you can compute exactly what the conditional probability is. But in general, you may have to resort to approximate inference algorithms. Excuse me for this background noise here. May be here for a while. So approximate inference is often required for more general and complex cases. Okay, so that's the whole kind of overview. But once we cover these techniques in the next lecture after Thanksgiving, then we will have a quick one lecture on estimating probability distribution. So the idea behind this is oftentimes you have data, right? So estimating because we've been talking about random variables and joint densities and density functions, but we've never, and we always assume it is given to us, but in practice, we do not know density functions. We do not know what's the probabilities of events. So if you have historical data, then that can actually help you to estimate those functions from the data. So we will have one lecture on this. And again, we will have two different techniques to do it. Of course, there are many more complex techniques also. Just to give you a teaser and diversity in the topics we've seen in this course. From data samples, so one of the techniques will be the maximum likelihood estimation. That's a parametric estimation technique. when I say parametric, means you assume that there's a model and there are parameters in the model, and the idea is to estimate those parameters from the data. Then we also have a maximum a posteriori. So it's called the MOP estimation. Okay, so now let me also write down a quick detail of the inference topics. Maybe I just wrote it generally, but we can have a more detail here. So what we will study is if you talk about exact inference, we will learn the variable elimination, technique. And for approximate inference, we will have the message passing algorithm. Or we also call it the belief propagation. So here's the roadmap that we will have in our remaining lectures for this course. And next week, as you know, is the Thanksgiving break. So I hope you guys will have a great holiday, and if you have time, you will work on your projects. So we are not having any kind of assignment for next week, but the week after we will have the homework due. So I'll release the homework today, and that will be due on the after the break. Okay. So, and it will be homework will be related to BaseNet. That's the end of our lecture today. Homework is on BaseNet and hope maybe MRF. I believe. And after that, we will have one more quiz and one more homework. Right, so I guess this is homework number 5 on these are short homeworks and not too complex. Okay, then we will have quiz 7 and then and kind of and homework 6. And a note, one homework and one quiz, or let's say just 6 quizzes. So best and the best 5 homeworks will be included in the final grade. Okay, so we will finish up early today, and I hope you have a great holiday. And any questions before we disperse?
I have a question.
Yes.
When is the final project due?
So I haven't posted the the link for it, but I'll assume it's somewhere around December 15. So it'll be after your last lecture, maybe a week after. Okay.
Thanks.
Yeah, thank you for reminding. I'll just put up a link for you to submit and also the date. Okay, anything else?
I just wanted to go over the homework too, Professor, after the class.
Yes, okay, you can stay and then the rest can leave.
I guess I have a quick question. When do we expect to get grades on the homeworks that we have turned in, 3 and 4?
I think soon, before the Thanksgiving break.
Okay, thank you.
Yeah. Okay, so let's stop the recording here, and I'll see you after the next week.